The network just made a prediction, and it was wrong. Backpropagation is how it learns from that mistake. The whole idea rests on one question. For each weight, should we turn it up or down, and by how much? Let's build the answer from the ground up. Here's where we are. Our little network predicted 0.78, but the true answer was 1. The loss function turned that gap into a single number, a loss of 0.25. Our job is to make that number smaller. Every connection in the network has a weight. Think of each as a knob we can turn. Which way should each knob go? Let's zoom in on one weight and ask a simple thing. How does the loss change as we turn just that one knob? If we plotted it, we'd get a curve like this, a bowl. Turn the weight too far either way and the loss climbs. Somewhere near the bottom, the loss is smallest. Right now our weight sits here, at 0.7, partway up the left side. The loss at that point is our 0.25. Now the key idea. Touch a straight line to the curve right where our weight sits. That line is the slope of the curve at this point. And that slope is exactly what we call the gradient. It measures how fast the loss changes if we nudge the weight up a little. Look at which way the line tilts. Here it slopes downhill to the right, so the gradient is negative. A downhill to the right slope means, increase this weight and the loss goes down. So the rule is simple. Step in the opposite direction of the gradient, and you always head downhill toward the bottom of the bowl. But most weights are buried deep in the network. How do we find the slope for a weight that never touches the loss directly? We follow the chain. Changing a weight changes its z, which changes the neuron's output, which changes the loss. Multiply those small effects together, link by link, and you get the gradient for that weight. That's the chain rule. Here's the clever part. We don't redo that chain from scratch for every weight. We start at the loss on the right and sweep backward through the network, just once. Each layer hands the layer before it the piece it needs. In a single backward pass, every weight ends up with its own gradient. That backward sweep is what gives backpropagation its name. Let's compute one real gradient, the easiest one, right at the output. For this loss, the gradient at the output is just the prediction minus the target. Take 0.78, subtract 1, and you get minus 0.22. Negative, exactly the downhill slope we saw on the curve. Now we take the step. The new weight is the old weight, minus a small learning rate times the gradient. That's 0.7, minus 0.5 times minus 0.22. The two minus signs make it a plus, so the weight climbs to 0.81. Watch the weight slide down into the bowl, and the loss drops with it. That single step made the network a little less wrong. And that's the engine of learning. Every weight gets its own gradient from the backward sweep, and every weight takes its own small step downhill. Repeat that over and over, across thousands of examples, and the whole network slides toward the bottom of the bowl, its lowest loss. That is training. In PyTorch, all of that hides behind a single line. You compute the loss, then call loss.backward. That one call runs the entire backward sweep and fills in a gradient for every weight in the network. You never work the chain rule by hand. So, backpropagation in 3 ideas. The gradient is the slope of the loss with respect to a weight. It points uphill, so we step the opposite way. The chain rule finds that slope for every weight in one backward sweep, and each small step downhill makes the loss a little smaller. Next, we'll meet the optimizer, the part that actually takes those steps, and takes them cleverly.